Okay, so let's get the program started. I am going to get to my presentation. I had to reboot my computer because YouTube decided to kick me out. And I am back up and running. We're going to go back to basics. Today's program is going to be on the single line diagram. I think one of the most important parts of a power distribution system documentation is the single line diagram for a lot of different reasons, which I'm going to cover. We're going to talk about the all of the key documents that reference the single line diagram, and all of the areas of the NEC, NFPA 70E, and NFPA 70B that make up that reference the single line diagram, or what we might call the one line diagram. So I like to look at the single line diagram as a document that gives you, it's like your roadmap to the power distribution system. So if you think about, if you're going on a journey, and let's say that I told you had to be in Weirton, West by God, Virginia in 2 weeks from today, and my question is, could you get there when you don't have a map or anything that tells you how to get there? You don't, or maybe I give you a map that sort of looks like this, and I told you you need to get to Weirton, West Virginia, and if you look up there where that golfer is, you're basically, you know where West Virginia is, if you can figure out where you're at, but you know a general direction. But the chances of you ended up in Weirton, West Virginia, especially if I gave you my address and you wanted to end up at my house, you probably would have a very difficult time doing it with that map. Or maybe I gave you this map, and you had to sit down and say, well, you know, you don't have the right information, because it's, you know, this looks like a map that was from the 19 whatevers, so it's not the latest document that you'd need to actually get anywhere. Or I can get you a map that basically gives you everything that you need to be able to get to the power distribution, to get to my location. And I liken that to the one-line diagram, because the one-line diagram, it's really important that you have the latest information that basically gives you the roadmap to your power distribution system. So the one-line diagram plays a very important role in a lot of different analyses that we do on a power distribution system. We will calculate short circuit currents, we'll do selective coordination studies, we'll do load flow analysis, and any other engineering studies, whether it be a power quality study, electrical safety procedures, and we're going to talk about the electrical safety procedures when we get into a 70E discussion, and even 70B from a maintenance perspective. That single line diagram is the start and the heart and soul of the beginning of a lot of engineering and electrical worker procedures. Now, I am going to use two different types of terminology. I have a single line diagram, and I've probably used both of these terms here in the last few minutes. I got single line, and we use one line. Needless to say, I know I am going to use that term interchangeably. I'm not consistent myself. I don't know that we have to be, but at least we'll understand what it is that we're talking about. Basically, the single line diagram is it takes all three phases of the power distribution system and basically puts it all into one line. So you're not looking at a very complicated system of lines, A, B, and C phases, etc. You're just looking at one line for each of the areas of the power distribution system. So the single line diagram is referenced in the National Electrical Code, NFPA 70B, and in 70E. I have the text for each of these areas from a document perspective that shows you those references and shows you how it's used. And we'll have that discussion as we walk down through here, because in the back of my mind, I was looking for where in any of these codes and standards does it say that you're mandated to have a single line diagram. And I was surprised at my findings, and I'm going to walk you through what I learned and see what your thoughts are. So the single line diagram is defined in 70E as a diagram that shows by means of a single lines and graphic symbols the course of an electric circuit or system of circuits and the component devices or parts used in the circuit or system. So, this was I think the only definition in any of those documents that I could really find. But I think it does a good job in explaining that, it's going to have graphical symbols, and we're going to talk about those graphical symbols and different components of devices or parts, which we don't throw every single component in a power distribution system on a one-line diagram, just some key elements. And I'm going to walk through each of those. So one of I guess I'll start up. You obviously have to indicate where the utility is, and you'll probably see drawings that have the utility transformer and any other transformer that's in the power distribution system. So transformers are a very important part of the system. And typically on a one-line diagram, you'll have at least some bare minimum information which will show you and give you an indication of the wiring of it, whether it's a delta Y grounded, delta. You'll have some sort of indication, because that helps us understand how the system is grounded, whether it's an ungrounded system, whether it's a grounded, solidly grounded, or an impedance grounded system. The little symbol that's right next to the transformer, that will give you an indication of the way the system is grounded. So the transformer is a very important piece of this puzzle. You can really determine how a system is grounded by simply finding a transformer, looking for that symbol, and finding out if it's a delta Y ground, and whatnot. So the secondary of each of those is really a critical piece of the pie. And then you'll have the kVA, and you'll have the voltages on the primary and secondary, and you'll have the percent impedance. So obviously the kVA is really important. Sometimes you'll have a complicated kVA that'll have OA, FA ratings, where if there are fans or if there's oil cooling, etc. But those, you'll have a lot of information with regard to that transformer. So other big components in a power system are your motors. So your motor information is really important, because that's going to be another fault contribution. It's going to have it's going to possibly contribute fault current. It could possibly contribute to harmonic content, depending upon if those motors have variable frequency drives. Normally, somehow you probably should indicate whether or not there are VFDs there, because that is another very critical part as well of the picture. So that's a detail that's important to understand what the harmonic content and whether or not you'll have fault current contribution. So adding the motor, and you'll have you'll usually have the horsepower of the motor there. The impedance of the motor is not typically shown. We make some assumptions when we're doing fault current studies and things of that nature based upon impedance, but you'll usually have the horsepower of the motor that's installed, especially the larger ones. Now, conductors are another area. Conductors rarely change in a power distribution system. Unlike motors, I may add and subtract motors. I may, I may not change out transformers as much as I might change out a motor, or add a motor, or subtract motors. But conductors, that's the glue of the entire system. That basically pulls all the components together. Very important piece of the pie. Typical information, what you'll typically see on a one-line diagram is you'll have the conductors, but I think more often you'll have a table of what the an indicator for each of the conductors. So a conductor might be labeled with a symbol or a number, and then there will be a table associated with it on the single line diagram that'll tell you all the pertinent information, including the length of that conductor, the size of the conductor, how many you have in parallel, and whether or not it could be busway as well. Again, the length of those conductors are really critical when we are in the design phases. A single line diagram, which is another interesting point, we create a single line diagram even before we've purchased anything or installed anything. But when it comes to conductors, we may not know the length of the conductor until after it's installed, and these drawings should be updated with what we call, we should create an as-built drawing, which will document exactly how many conductors they put in phase with each other, what the length was, and all of that good stuff. Anything that may have changed from the design phase. And the same goes with transformers. Since we haven't bought a transformer yet, the impedance of the transformer that you may see on a drawing that's in a bid package or something of that nature is going to be you'll have the kVA, you'll know the voltage, but you're not really going to know the percent impedance. You'll definitely know if it's a delta or Y grounded and how it'll be wired, because the grounding of the system will dictate that. But some of the information during the as-built or during the initial phases of a project, those diagrams are not going to be accurate until we get them done and we get things installed. Another important part are the overcurrent protective devices, whether there be fuses or circuit breakers in the system. There are different symbols for fuses and fuse links, and different symbols for power circuit breakers, medium voltage circuit breakers, and low voltage molded case circuit breakers. So you'll typically see, as you get savvy in the world of the one-line diagrams and some of the symbols that they use, you'll get to recognize exactly what type of overcurrent protective device is being installed or being planned for that installation. So the other, we put on all of the major components on a one-line diagram, and some of the information pertaining to those components. Some I might have a little bit more information on the one line than others, like we talked about, large motors versus smaller motors, transformers. I won't put typically control power transformers and other little logic. There will be other focused single line diagrams for different types of and parts of the distribution system. And I wouldn't confuse a one line diagram with what we call a schematic diagram either, because a schematic diagram is something that we would typically see like inside of an industrial control panel or things of that nature, that tells us how a piece of equipment is wired up. I'm not talking about, in this discussion here, I'm not talking about a schematic. I'm really talking about the power distribution system single line diagram. So now a complete single line diagram in conjunction with a physical plan of the installation, it really gives you enough data to plan and do an analysis on the electric power system. And the reason I say in conjunction with a physical plan, in some cases you may not know, like say a length of a conductor. If you're trying to estimate in the beginning levels of a project, you may not have the actual installation. But if you're doing short circuit studies or selective coordination studies, and you don't want to be the most expensive guy on the block when you put in your bid, you're going to want to make some estimates on conductor lengths, because if you go too long of a conductor in the planning phase and the actual as-built drawings say that the conductor is shorter, you know that shorter of the conductor will give you higher fault currents. That may have led you to pick the wrong equipment, either from a selective coordination perspective or from a perspective of interrupting ratings of overcurrent devices or short circuit current ratings. So you want to be conservatively short on your conductor lengths, but you may be able to use the plan views to try to figure out how far away your equipment is from each other. And then you have the single line diagram conveys, again, the overall scheme, details of all the different elements of the distribution. You'll know what is normally open, what is normally closed, and when it comes to tiebreakers and things of that nature. All of that's going to be very critical and important, especially when it comes to for the electrical safety of the electrical worker. will show the utility supply, any of the cables or busway, all of your switch gears, panels, junction boxes, etc. Any of your protective relaying devices and your overcurrent devices, that'll all be indicated on there in some fashion. You'll get into relays in the medium voltage, and so you'll typically have like maybe a circuit breaker or a switch that's being shunt tripped from a relay, and typically you'll have a symbol to indicate that that's the case, that there's a relay involved there. And then you'll have all of your symbols, any of the breakers that are normally open or normally closed. The really complicated drawings that you might run into regarding the complexity of switching in a system. I would say a good example would be your data centers, because a data center will have a lot of backup power and different ways to configure the system. Configuration of the system is really critical. You should be able to look at a single line diagram and determine what is open when, so that you know, for example, if you're doing lockout tagout, if you're going to work on something in an electrically safe working condition and you have to create an electrically safe working condition, you need to know what to lock and tag out, and what might turn on. If you don't understand that through the one-line diagrams, it could lead to a safety concern. All right, so that's from an example of importance of a one-line diagram. I used this in a previous presentation of mine. This panel board that we're looking at on the secondary of this transformer, usually if you look at panel boards, working on a panel board, doing justified energized work, you turn the main off, you suit up, and for the most part, panel boards are probably going to be downstream of a molded case circuit breaker. That's typically, if you're working on panel boards, the chances of you working downstream of a molded case circuit breaker are pretty high. And we could use NFPA 70E practices and whatnot. But in this case, you would know that this panel board is at the secondary of a transformer, which changes the game a little bit, because whenever you have a panel board on the secondary of a transformer, your next upstream overcurrent device is the overcurrent device on the primary of that transformer, which is at a different voltage level. The through fault current is going to be much lower. That primary breaker is set at a higher value to allow inrush currents. So you're in a unique situation in the power system when you're at that first panel board on the secondary of a transformer. The one line is going to tell you that. Now, if you're lucky enough to have a label on that panel board, you'll know that in this case it's 23.5 calories. But if you were working on a main lug only panel that had a separate overcurrent device just upstream of it, and you're still downstream of the transformer, but you have the advantage of having this breaker in a box or a fusible disconnect that you're looking at, now you know your incident energy is going to be much lower. In this case, it went from 23.5 down to 0.34, which I think is a big deal. And if you manage to put a fusible switch in there, you're at less than a calorie in both cases, whether it be a circuit breaker or a fuse. You've considerably increased or decreased the likelihood of having a huge event in that panel board. But knowing that and looking at the one-line diagram, I think is one of the important messages here that I'm trying to convey. And then obviously, there's the breaker integrated transformer. It's just a solution that I think is absolutely awesome, that will decrease the incident energy at that first panel board on the secondary of that transformer considerably, because you're taking advantage of not the overcurrent protective device on the primary of that transformer. You're taking advantage of the first overcurrent protective device on the secondary of that transformer, which will considerably reduce the incident energy at that first panel board downstream. Now, the one-line diagram is your roadmap to get to your final destination, and without it, in my opinion, you are lost. It's like working without a safety plan. I asked my cousin one time the importance of in his mind, what's the importance of the safety plan? And he said, if you don't have a safety plan, you're flying by the seat of your pants. And he's right, and I would apply that same phrase to the single line diagram. If you don't have one, you're flying by the seat of your pants. So let's take a look at 70E and the references in 70E. We already talked about the definition that they have in 70E, so I'm not going to go over that again. But if you look in 120.2, the lockout tagout principles tells us that a lockout tagout procedure shall be developed on the basis of the existing electrical equipment and system, and shall use suitable documentation, including up-to-date drawings and diagrams. So it says you shall use suitable documentation, including up-to-date drawings and diagrams. It doesn't say you have to have an up-to-date drawing and diagram. Now, I'm going to use that term, that phrase. It doesn't say that you have to have it, because I'm hoping that somebody out there decides that, this probably deserves a public input. In my opinion, it does. The more people that tell the 70E panel that they really need a requirement that you have an up-to-date one-line diagram or single-line diagram, I think it's critical. But in this case here, it just says it shall include. It doesn't say it must include. And shall use suitable documentation, including up-to-date drawings. So documentation, so in the electrical circuit interlocks, documentation including up-to-date drawings and diagrams shall be reviewed to ensure that no electrical circuit interlock operation can result in re-energizing the circuit being worked on. So you're going to need documentation, and it says up-to-date drawings and diagrams. When I first started out of college I graduated in '90, and I was doing a systems analysis study at a plant down in Tennessee for a very large manufacturing facility. And my first step was to, I had the one-line diagram, and I was just doing some verification. The PE I was working under told me to go take a look and just verify some of the parts. I was looking for a motor control center, and I'm walking around that facility, and I realized that I can't find this motor control center. And when I'm walking around and I'm looking for the equipment, and I can't seem to find the drawings or I got the drawings, I can't seem to find the equipment. Or there was an electrician sitting there on the bench, and he goes, "What are you looking for?" I said, "Well, I'm looking for MCC3AB." I said, "It's supposed to be here on this mezzanine, but I've been here numerous times, and I checked downstairs and I checked upstairs." And he looked at the drawing, and he goes, "Boy," he says, "this is from 1971. He goes, "This is an old drawing." He says, "I was here when we took that motor control center out." And the drawings had never been updated. So I was supposed to do a short circuit and coordination study for that facility, and we bid the project that way. When I showed up on site and found out that the drawings weren't updated, now we went into an entirely different mode, because I had to have an updated one-line diagram. We had to go back and we had to pitch to the customer the issue that I could not do an accurate analysis without that. So then we had to change the order and the scope of the project to include a complete walk down, and we hired a group to go in and do that. But that is a piece that I think is really important, that we make that a priority for us, because if we don't, then we really can't do the analysis that we have to do on these projects. So it's just a critical role, and it must be kept up to date as it's talked about here in 70E. So the lockout tagout principles tell us that we have to determine all possible sources of electrical supply to the specific equipment, and it says to check applicable up-to-date drawings, diagrams, and identification tags. It talks about that after proper interruption, we have to determine what caused the device to open. So I've got to know, what am I serving? What are my power? What if I look at a breaker that opened, and I don't know if it interrupted on a short circuit or an overload, I've got to figure out before I close that breaker. I need to go figure out why it tripped. Well, I can't do that without knowing what loads it's serving, and that's where the one-line diagram comes into play. It tells us that for, again, establishing and verifying electrically safe work condition, I've got to release any block or stored mechanical energy. I've got to release any stored electrical energy, apply lockout tagout devices, and it says use adequately rated portable test equipment. So I can't apply lockout tagout devices if I don't know what I need to lock out and tag out. So the one-line diagram is critical throughout that whole process. So also in 70E, we go up to Article 205, talks about general maintenance requirements. Now here's another reference to the single line diagram directly. It says a single line diagram where provided So it doesn't say a single line diagram shall be provided. It says where it's provided for the electrical system shall be maintained in a legible condition and shall be kept current. So 70E tells us if you have a one-line diagram, which every one of these systems are going to have a one-line diagram, we have to keep it current. That is a critical role, critical part of the success from a safety perspective. Now, in 340.5 of 70E, where it speaks to employer responsibility, the employer has to be responsible for the proper training and supervision of qualified personnel. And if you look at item number 6, the provisions for complete and accurate circuit diagrams and other established information to the employee prior to the employee starting work. So, they need to provide the electrical worker with the information they need to be able to determine lockout, tagouts, and all these other good things that 70E is really telling us that we need. And here in 340.5, they put the responsibility on the employer. And if you think about it, that's the facility owner, and all of these details with regard to that single line diagram need to be handled before we step foot out of the truck at a job site, because if you don't have those updated one-line diagrams, again, you're flying by the seat of your pants. You don't know what you're walking into. You really need to have those diagrams, and they have to be kept up to date. Now, in Annex E, we talk about from the electrical safety plans perspective. It tells you your electrical safety program procedures can include, but are not limited to, determination and assessment of the following. So it says it can include those. It doesn't say it shall. It says it can include those. And number 9 on that is the electrical single line diagram. So from a 70E perspective, those were the areas that I could find in 70E that reference the single line diagram. I think you understand why it's defined in 70E in 100 of 70E, because that's where it's used multiple times throughout that document. Now let's take a look at 70B. 70B, again, is the recommended practice for electrical equipment maintenance, and I'll just make a plug here from a NFPA perspective. I'm on the 70B committee, and we are feverishly working to move this from a recommended practice to a standard. This document is going to move from a you can and you could and you should to a document that says you shall. And in my opinion, that really hammers home the trilogy. And I refer to the National Electrical Code, NFPA 70, the recommended practice for electrical equipment maintenance, NFPA 70B, and electrical safe work practices, NFPA 70E, as the trilogy, because they all work together. I have to install things correctly, and I have to install things correctly, and I have to maintain things properly to ensure an electrically safe working conditions. I see a question came in. Is there a universal symbol chart that you can recommend or share? Depending on where you're located in the world, drawing symbols tend to differ. And I agree with that statement, Anand. I'm not sure what part of the world you're in, but I know there are some IEEE reference materials. I maybe at the end of this, I'll do a quick look out on the IEEE website. If you are I don't know if you're an electrical engineer or not, but if you are an electrical engineer, IEEE has some really good references if you're a member, and especially a member of the IAS Society, the Industry Application Society. They have a lot of good resources that I believe if you're an IAS member, you can go online and take a look at that. I don't know, Nihad, you're watching this as well. You're an IEEE member. I don't know if you're familiar with a document, if you can comment on that, that would be awesome. Otherwise, I'll have to do that research a little bit later. So 70B is an important document, and here's some references. The availability of up-to-date and accurate and complete diagrams is the foundation of a successful electrical preventative maintenance program. That is a very important statement in 6.2.2 diagrams and data of 70B. And I agree with it 100%. I'm looking at the wrong slide, but 6.1.5 talks about single line diagrams as maintenance. I was looking at the next slide. Here's my statement I was just referring to. 6.2.2 talks about diagrams and data, telling us that the complete diagrams is really your foundation. So that just really hammers home in my mind that the single line diagram, even from a maintenance perspective, you need to know what you have and where you have it. And every time you get into doing maintenance, so a lot of people say, well, I never had time to keep my one line diagram updated. And I think that that's a cop out in my opinion, because anytime you're doing maintenance, if you didn't have time to make that means you probably didn't have time to do your maintenance on your program, on your power distribution system, because while you're doing maintenance is a great time to keep those documents up to date. Anytime you're in a piece of equipment, if you're in your main switchboard and you have all of those overcurrent protective devices, check the settings on the overcurrent devices. Check that against your short circuit study and your coordination study. Keep that information flowing and keep it fluid. That one line diagram should be a living document in your plant. Keep it updated. So it is the foundation of a successful EPM program. And I would say a foundation for a successful electrical safe work practices program as well. So in the 70B has a specific section, 6.2.2.1, which is focused on the single line diagram, and it tells you that sort of what it have on it. It should have all of the electrical equipment in the power system, and give any of the pertinent ratings. Now that's a term that we use. You may find it very pertinent to put the impedance of a motor for whatever reason in your facility. But may not be pertinent for me to put the impedance of a motor on my one line diagram. So what is pertinent and to you may differ from facility to facility, which is I think why single line diagrams, they are not all exactly the same. Normal operating positions should be included. So if there are overcurrent devices that are normally closed or normally open, switches that are normally closed or normally open, that's important to make sure that information is reflected on the one line diagram. And again, additional diagrams appropriately noted in the main diagram can be drawn. So what we'll typically see is references to other drawings. Now we'll take a look at the National Electrical Code. So we've been through 70B, and now we're moving into the National Electrical Code. Now in the NEC, we have just a couple references that I could find. I think this is the only one actually that I was able to find in the National Electrical Code, where it talks about installations where the possibility of backfeed exists shall comply with A and B, which follow. In B, a permanent and legible single line diagram of the local switching arrangement, clearly identifying each point of connection to the high voltage section shall be provided within sight of each point of connection. So I think you'll typically see a one line diagram in the main switchgear room, probably posted up on the wall and whatnot for these reasons. So, installations where a possibility of backfeeding exists, you're going to need, as part of B of 490.25, a permanent and legible single line diagram. So that's like the only requirement, dead on requirement that I could find in any of these documents. And that's about the only reference I could find on single line diagrams in the National Electrical Code. But we know that the NEC requires us to do short circuit studies, and it requires us to do coordination studies. And to do that, I need an accurate single line diagram. So an up-to-date single line diagram is vital for a variety of service activities, which include the short circuit calculations, coordination, load flow studies, safety evaluation studies, all other engineering studies that you're going to possibly do on a power distribution system. You really need a single line diagram. And your electrical safety procedures and maintenance, as we covered in 70E and 70B. So my word to most facility people, if you're an electrical contractor, if you're an electrician, if you are in the business of providing a service to your customers with regard to the electrical distribution system, I think that making a quote, quoting, quoting. Say you're going to do a project and you're on site with the customer and you're going to install some equipment. My suggestion is please make that an offer to your customer that you can keep their one-line diagram updated. If there's anybody in the best position to do that, would be your design build contractors or your engineering firms. I mean, if you reach out to your customer, build a contract around their power distribution system, and in such a manner as to say, look, we're going to maintain that one-line diagram for you. We're going to keep it updated. We'll continuously, any changes, you should be doing an arc flash analysis study. You should be doing a short circuit study. If you have a lot of harmonics and harmonic drives, or if you've installed filters, you're going to constantly need to make sure that your power quality analysis is up to date. You don't want to create series resonance and other issues because you're changing the power distribution system. So those are all very important things that, and ways that we can build the relationship with our customers and facility owners and take that burden off their shoulders, because we really need to keep those one-line diagrams updated. And if they understand the importance of it. So if you take this type of a video and say, look, we have 70E, 70B for maintenance, and we have National Electrical Code requirements as well, all raising the awareness of how important the single line diagram is, you'll have a better chance of maybe helping that customer achieve their safety goals by keeping those documents up to date. So now what I wanted to do in this next phase of this is I wanted to just walk into what we call the impedance diagram. Now, I'm a power systems engineer, and I've done a lot of short circuit and coordination studies. And the first step of that is to create a single line diagram. And normally we take the single line diagram and we put that into a systems analysis software like what would you call it? SKM, EDSA, Easy Power, any of those types of systems where we load the one-line diagram in and then we will perform studies off them. Now, I think it's really important to understand what those software applications are doing in the background. And anytime you have a conductor, if you have a motor, you have a transformer, these are all impedance values in a power distribution system. And understanding that is important because that helps us understand what the impact of adding conductor length or subtracting conductor length, adding motors, etc. to the power distribution system. So really, the impedance diagram, what we call the impedance diagram, is the next step of the single line diagram that typically an engineer will create. Not necessarily, you won't have electricians and things of that nature conducting the impedance diagram. You'll have your power system engineers that will be looking at the system with regard to impedance. So I want to walk through that because I think it's an important aspect to understand the importance of the one line diagram. A single line diagram, all the major components are put on the single line diagram. It's our tool, right? We already said that. And most of the power systems studies are going to be converting this information in the background to an impedance. So every one of these components that I'm showing on this screen, those fuses, they could be, but we don't typically represent those as an impedance, but conductors, transformers, motors, busway, all of those components are basically can be represented as an equivalent impedance, whether it be a reactance only, a resistance and reactance, or just a resistance. But not every one of those components, we don't typically convert and represent fuses. We don't take the bus inside of a panel board and represent that as an impedance on the system. But we're creating our circuit, basically. If you think about it, it's just a large circuit. So first thing you have to understand is your impedance, and then look at each of the major components and say, how do I turn those into a resistance, an inductance, a capacitance, or maybe it's a combination of both of those. So utilities, transformers, motors, conductors, and generators, all of those will be converted into impedance. Now, not every one of our power distribution systems are resistive. I think most of the people watching this will probably understand that any component can be probably represented either by a reactance only or a resistance only, or maybe a reactance and a resistance. And basically what we're doing is we're creating what we call the power triangle. If you're familiar from a power triangle perspective, you have real power across the bottom, reactive power up the side, and then you have your apparent. So you have watts across the bottom, you have VARs up the y-axis, and then you have VA across from your hypotenuse, basically, of that triangle. And then the angle of that triangle is your power factor. And we use this triangle. I mean, I'm planning to do a web event just on complex variables, just on this power triangle to help us understand the power of that. It's not my intent here. I just want to make sure that people understand that various components will have different parts and fill out different parts on this power triangle. You might have something that's resistive only, and you might have something that is you might have something that is just resistive down here, or just reactive up the side here, or and then if both of those can be represented as a Z, and I'll even show you in the National Electrical Code where we use those exact same technologies, or the exact same terminologies in the NEC. Now, your highly inductive components are transformers, reactors, and motors. Now, I noted here that, when we model a transformer, we don't model we normally don't model a resistance. We just assume that it's all reactive. That's why we have a percent impedance. That X per unit impedance is really just the X. We'll make an assumption to try to get to resistance sometimes, but we'll usually model it as just an X and not a resistance or an impedance Z. Reactors are pure reactive, obviously. Your motors are very much like a transformer. If you think about a motor, I mean, there's a lot of iron there, and you've got windings around an iron. And think about a transformer. You got the same basic principle going on. You've got windings that are copper, and you have an iron core to that transformer. Now, their highly resistive components are your heaters. Now, this is going to be all resistance, basically. Your heater elements, those are resistive elements that you're turning on and you're heating them up. So that's almost as pure resistance as you can get. Your incandescent light bulbs, which we rarely see anymore in our power distribution systems. But your incandescent light bulbs, those are typically purely resistive. And in that case, you wouldn't have any of this reactance. You don't have a Z at all. Your value is just this horizontal at a zero angle. And that's basically how you do your power triangle in that case. And then you have your conductors. Your conductors are typically resistance and reactance, and you'll have an effective impedance Z with regard to in conductors. And I'll show you in Table 9 in the National Electrical Code reflects that. And we'll use this information for voltage drop. Now just think, if I was doing a voltage drop study and I used Z, the length of this hypotenuse is much longer than the length of my resistance side of this triangle, and the length of this is much longer than my hypotenuse of my reactance. Now, if I'm doing a voltage drop study and I'm using Z, I'm using basically the longer portion, so my voltage drop would be worst case. If I based my calculations just on the magnitude of that vector right here, this Z number. If I based my voltage drop calculation just on X, obviously I'm not considering resistance. I'm going to come out with a lower voltage drop than if I used the Z, because I'm not using a very large number because it's the smallest part of this entire triangle. So the most accurate calculation for, like, say, voltage drop or short circuit is when we include the R and X in our calculations. Now let's just talk, since we brought up conductor impedances, and we already said that conductor impedances have both a resistive and a inductive component to them. In some calculation tools, like for example, some of the short circuit calculations will use X only to simplify things. I won't get into the complex math on how to add these things together, but some of your software tools will use just the X only to simplify things. And if we look in Table 9, you'll notice Table 9 has it's called the alternating current, resistance, and reactance for 600 volt cables. So this is a table that has resistance and reactance. And now you understand what resistance and reactance is related to the power triangle. And you'll note that it's ohms to neutral per kilometer, or ohms to neutral per 1,000 foot. Always use the right numbers in the bottom of this slide, else you will be working in Canada instead of the U.S. And using the wrong numbers. Down the left-hand side of this table is the size of the conductor. And then the body of this, you'll notice that you have X sub L, which is the reactance. So the reactance is the y-axis of that power triangle. So that's up the side. And you'll note that these are the values, whether you're in PVC aluminum conductors or in steel conduit. Those are you'll have two different numbers, so you have to know where your conductors are being routed, if they're in steel conduit or if they're in PVC, and remember to use the right the right number, whether it's the top one or bottom one, because again, the bottom one is your ohms per 1,000 foot, the top one is your ohms per kilometer. So just don't. I've seen that mistake made multiple times. And then again, there's your there it is there. I knew I was calling out somewhere. So use the bottom for ohms and the top for 1,000 foot, and the top for ohms per kilometer. And then you have the resistance. So this is across the bottom of that power triangle. This is your resistance for uncoated copper wires, and then you have your resistance for aluminum wires. So you have copper and aluminum, and you'll notice that we don't have aluminum numbers for number 14. They start at number 12. So you'll have all of the information. Again, you'll have a resistance value that could be different for PVC, aluminum, or steel. So you have to know again what you're routing it in. And then again, there's your effective Z. Now, if you didn't know what effective Z was before, now you know. Go back to the power triangle, and that's the hypotenuse. And they'll give you at a power factor, because what did we say? We said that you had, if you think about the triangle, that angle on that triangle was your power factor, and that establishes the height of the X. So when I say a 0.85 power factor, I'm establishing an angle. I can tell you what the resistance is. We're giving you the Z. At an angle, we can determine the other two sides of that power triangle if we wanted to. We would typically, if you look and say, well, why would we have effective Z and where would we use it? Then we go to the notes. And it tells you that these values are based on the following constants, that there are HH wires, Class B stranded, conductivities are 100%, capacitive reactance is ignored, and the resistance values are valid only at 75 degrees C, etc. for 60 hertz. Now, granted, if you change any of these parameters, the impedance is probably not going to change all that much, but it could. It could. Effective Z, there's your effective Z that we were just looking at, is R. And there's your R cosine. I'm going to do a program that just helps us understand that equation, because it is powerful, absolutely powerful. There's so much you can do when you know the power triangle, and I'll definitely have a program on that. We'll do one of those on YouTube maybe. Multiplying current by effective impedance gives a good approximation for line to neutral voltage drop. Okay, so it gives you the approximation. And remember what we said, if I'm doing a voltage drop and I'm using the Z, that's the longer part of the triangle. So if I do a calculation based upon that, my voltage drop number will be greater. I'll have a greater voltage drop because my impedance is inflated a little bit, so it's conservative. If I get that to work with my voltage drop, and if I decided to do the R and X and do the long, complicated math, my result is going to be a voltage drop that is less because my effective impedance will be less than that large hypotenuse Z. So that's another important data point to understand why it's used in the National Electrical Code that way. And they pick 8.5 because that's typically most of your loads, all your motors and things like that. The power factor of those motors are pretty much going to be in that ballpark anyway. And because of the conservative nature, the length of that hypotenuse Z that you're using, any error that you might have, if the power factor is better than what you thought it was, you're still going to be covered because you're using the longer portion of that triangle. So, and if I asked you the question, what's the impedance of a 200-foot length run of 2-aught aluminum conductor in PVC? This is how you would find it. You would select the 2-aught conductor over here. You would look for PVC, okay, and I said aluminum, so there's my aluminum. And I said in PVC, so there's your PVC aluminum, and that is my X sub L, my reactance. And if I'm in Canada with Nihad El Sharif, I am looking at the top number, the 0.141. If I'm in the U.S., I'm looking at 0.043. If I wanted to know, that's the X. The R is the resistance. Again, aluminum wires because I'm aluminum, and I'm looking at in PVC, so I'm looking at that column right there. That's how you come up with the data for the impedance of that run of conductor. And then Z is 200 foot. I have to always remember, I've got to convert this. I said the impedance of 200 foot. So it's not, this is all per 1,000 foot. So I have to multiply 200. I have to take 200 divided by 1,000, 200 divided by 1,000, multiply that by the numbers I got off the table, and this 0.032 plus J 0.0086, that is my resistance is 0.032. My X is 0.0086. That's the, and you can see how small of a resistance that really is, or impedance that really is. So conductors play an important role in the power system, increasing or reducing fault currents. Paralleling conductors cuts the impedance in half. Adding length decreases fault current. Reducing the length increases fault current. And changes made due to voltage drop or ampacity adjustments can impact your fault current. It's very important. It's all clear as mud, right? All right. Okay, so we went for just about 55 minutes, and I'm going to take a look at some of the questions. I saw Nihad doing some work there. He was doing some research. Let's just do... all right, so we're going to do a quick look. We got, there's a symbol document that is more international. Okay, so Nihad's taking care of Anand. Thank you, Nihad. You're the man. David Engelhart. All right. Any questions? You can put them in the live chat. Anything that we can help you with? Because if not, I don't have anything else. This was my first live YouTube stream. Please let me know if it was okay. Here we go. At what point of the project does a selective coordination study get performed and submitted to the AHJ? Is it at all possible be conducted and submitted prior to, during, or after the install? Okay, good point, David. So here's the thing with regard to selective coordination. When I'm in the bidding process, I have to make sure that I quote the projects correctly. And in the process of trying to figure out what components I need to supply in a job to meet the requirements of say, Article 700 for selective coordination, because circuit breakers are so dependent upon fault current, I'm going to need to make some assumptions. So for me to quote the project, I will have to provide some data to a power systems engineer to help me pick the overcurrent devices. So I'm going to make some estimated lengths of conductors and things like that to bid it. What the inspector should be looking for We have a form out on our Busman or our Eaton site. I'll tag it on to the bottom of this video afterwards for selective coordination. We have a form that the inspector really should be telling the engineer to fill out to give you whether or not you're going to meet zero point 0.1 seconds or selective coordination, all currents, all times, and whether or not they're going up through the main or if they're going up through just the generator, all those details. You're going to want to get something from the design engineer to say, I'm designing this to meet those requirements. Because here's the problem. If they don't design it to meet those requirements, and you come on the job site after the fact and say, let me see your selective coordination study, and you look at it and you go, well, I see that you're only doing 0.1 seconds, but this is an Article 700 system, and you can't do 0.1 seconds, then to fix that problem is expensive, and it can be a challenge. You need to start with selective coordination in mind to meet the code requirements, but also to address incident energy issues should you have any. So my suggestion is that the AHJ give a form to the engineer or request a form from the engineer saying, are you designing this to meet the selective coordination requirements? Get that up front. Because if you don't get that established up front, fixing it afterwards is a chore. You can catch some of this in plan review. It should be on a drawing. A lot of times they'll put the notes on the drawing to say, I'm selectively coordinating per the National Electrical Code, all devices to selectively coordinate to the maximum available fault current. Put that on there. So the other issue that I have is we'll say has to coordinate. What I end up with is dialogue or requirement specification language that's very generic. And my sales guy doesn't want to lose an order. Neither does the GE, Siemens, or a Square D sales guy. So what they'll do is they'll say, well, I'm going to quote them a 0.1 second because, maybe no one's enforcing it, or I don't know what the local state jurisdiction is doing at that point. So they don't want to lose the order. They'll quote it that way. And then if things come around and they say, well, no, we're going to do things differently, then, then it's a fix in the design phase. But once it gets built, that's not a time to catch selective coordination. You've got to do it up front. So I would ask for that form. I'll put a link down below in the description of this to the form that I would suggest using for selective coordination. Hopefully that answered your question, David. Anything else? We're at 59 minutes. We're right at 1 o'clock. I started a little bit late because I had to reboot my computer. But I think if there's no more questions, we'll sign off of this program. All right? Thank you for watching. Please subscribe because I'm going to do more of these. And so subscribe to my YouTube channel. And we will see you hopefully as we fight this virus together. Keeping our distance, a part of the social distancing network. All right? Thank you very much, and take care. I'm going to sign off.